for method 1, we use state representation. So that means we're not solving the second order ODE, we're solving this condition, this system equals to plus oh, I think I have it wrong. X dot equals to AX plus BU. And then you know the initial condition of X naught. All right. So for all the method number 2, we directly go to the ODEs. So in that case, you have X double dot times M plus KX equals to 0. And then you know the initial velocity. You also know the initial position. So in these cores, we never add damping to the left-hand side. And then we don't have force terms on the right-hand side. So in practice, most of the time you're dealing with is something like this. So for the first, if you want to learn method 1, that can actually be easily done. It can be easily done. So if you use the second option, then we need to play some tricks. So those tricks are, I think, is too much for this course. We won't learn that. So if you do see something like this, that means you need to go to method number 1. Otherwise, either method should work for you. All right, so let me give you a few examples. So method number 1.1, so we need to use ODE 45. We need to find the numerical solution. So inside of the ODE 45, you need your ODE equation, you need your time span, you need an initial condition. And then these ODE 45 works for these most general ODEs. And also, it actually also works for nonlinear systems. So I would say ODE 45 is the most general method. It can basically solve any questions, but then the limitation is no analytical solution. You just cannot, you can only get a numerical solution in time domain, but no analytical solution. So let's see what we can do to learn that. So I'm gonna use these homework number 1 as an example, all right? Share screen. So lecture 20, homework number 1. I give you the mass matrix, I give you K matrix. And then in this case, I just want to make my code general. So I put my C and F there, but actually you don't have to put them here because they're all 0. We know the initial position is 1, 0, 0. Initial velocity is all 0. So how can we use the ODE 45 to solve this question? So first of all, you just input all these matrices into MATLAB. So a few things here. You can directly use the diagonal function to easily create a diagonal matrix. And the first part is because, as I said, for method number 1, we're not dealing with ODEs directly. We need to work in the state space domain. So that's why we first need to convert your second order ODE to state space representations. So what you do is, here is the code. So you just, for the first row, you just fill in zeros and the identity matrix. In the second row, you just fill in these two. All right, so that's how you construct your A. If you don't remember how we get this A, you can go back to the lecture notes. I have the equations there. And then for ODE 45, you need to define the time span. That means within which time span you want to find the numerical solution. So the line space means linear space. So we want to match our time span from 0 second to 20 second, and we have 1,001 time points. So that's about 0.02 second, which is more than enough. And your initial condition for your state variable, and that depends on how you define your state vectors. So in this lecture, I prefer to put position first and then all the velocities. As I said, by doing so, you can easily define your A matrix using matrix operation. You don't have to express, you don't have to expand all the equations out. So that can save you a lot of time. So your ODE 45, which is the first input of this function, is you need to find out the changing rate of your state variable. Basically, you need to find out the y dot. And then you need to describe your y dot as a function of time and state vector y. So here, your y dot is just A times y. The second part here deals with any external excitation, because in this case, we don't have any force term on the right-hand side. So it's just all zero. So if you do have forces, then you need to add your force function to replace one or more of these zeros. How to do that? So you can go back to the lecture. I can give you an example about how to use this method for forced vibration in, I think for homework number 3. So after that, you just have your T out and then your Y out. Remember that your Y out will be a huge matrix. As you can see here, if I move it on, you can see it's 1,001 by 6. So that means it has 1,001 rows and 6 columns. So each row means 1 time spot you have, because we have 1,001 time spots. Each column means 1 state variable. So that means from the left to the right, so we have x1, x2, x3, and then x1 dot, x2 dot, and x3 dot. And then if you want to plot your first solution x1, then you just need to find the first column. So that's the solution you have. All right, so that's ODE 45. It's very, very similar to what you learned for the single degree of freedom system. It's just your A matrix is even bigger right now. Previously it's 2 by 2. Right now it is 6 by 6. All right. So the second method for state vector for state representation is using Laplace transform. So we already learned this before during the class. You just define it uses sims s to define a symbolic variable s, and then you just do Laplace transform for your a y dot equal to ay plus bu, and then you just do Laplace transform your s. Your y dot becomes si times y, and then it's y ays plus bus. So the subscript s represents Laplace transform. And then you can move things around. You find your ys equals to this. So this ys is the solution in S domain. Once you find the solution in S domain, you just use I Laplace for ys, and then you can get your solution in time domain. So this method is super straightforward, really, really easy. I don't even want to go over this. So you can check my MATLAB code. But then the major limitation for this method is, I need to emphasize limitation. It won't work for every case or problem. So inverse Laplace transform, it only works for some simple systems. If you only have 2 masses or 3 masses in the system, it might work. But if you have thousands of masses, this one is either very time consuming or is really, really slow, or it's just impossible to find your solution. So I would say you can give this a shot, this method a shot at the beginning of each problem. But if that doesn't return an analytical solution in time domain, just don't force it, because that's the limitation of this method. You won't be able to find a solution. All right, the last one, which is the eigenvector and the eigenvalue problem. So what you do is, first of all, you also find the state space representation, y dot equal to ay. So in this case, we ignore any force, no force excitation. And then y dot equal to ay. And then what you do is, instead of working everything in y domain, you want to work in the q domain. So what's special for q domain? So in q domain, all the equations are decoupled, all right? So from y to q, you just multiply everything by p invert. And then from q to y, you just multiply everything by p. So that's why we call p is called the so-called coordinate transformation. And then the equation in your q domain is q dot equals to lambda times y. Oh, sorry, times q. Remember that your lambda is a diagonal matrix. Matrix. So that's why eventually you just have q dot equals to lambda 1 all the way to lambda n q. And then you just need to solve these equations individually. All right, so the most straightforward way to do these is you create a for loop. For loop is from I equals from 1 all the way to the last dimension, n. And then for each dimension, you solve your qi equals to e to the lambda I t times initial conditions qi naught, and then end. And then in the end, your q is just solutions of q1, q2, all the way to qn, right? So you create a for loop for each I, for each entity, you find the solution, and then eventually your total solution in vector format is just organize all these individual solutions row by row. So in this lecture, I try to teach you some more advanced MATLAB skills, which means, so the short statement for these is, if you do see a for loop, if you have a for loop in your MATLAB code, you can always use matrix operation to replace that for loop. If you only have 2 for loops, so that means if you have 1 for loop, you can always use a 2D matrix. If you use 2 for loops, then you can use a 3-dimensional matrix. If you have a total 100 for loops, then you can use a 99-dimensional matrix to remove all these for loops. So why we don't want for loops is because for loops are really, really slow. For example, in this case, if your n is 100, then you have to repeat these 100 times. But then if you use the matrix operation, you get the solutions in one shot. So I'm gonna explain this matrix operation a little bit. So eventually, in the Q domain, let's recall what we have for the Q domain. So in the Q domain, you have Q dot equals to lambda times Q. And then your Q solution is just Q1T, Q2T, all the way to Qnt. All right, your lambda is a diagonal matrix, lambda 1, all the way to lambda n. We already know that your Q, you already know the initial condition of Q. That's just Q1 naught, Q2 naught, all the way to Qn naught. And we also know the solution of Q is E lambda 1 T Q1 naught, E lambda Q T Q2 naught. Right? So that's the solution we need to find out. The easiest way to do this is create a for loop. And then make sure your entity or your variable I goes from 1 all the way to n. For each I, you can calculate E lambda I T Q I naught. And then you end this for loop and then arrange all these solutions. That's your Q I T. And then you organize all these QIT row by row in a column vector. But as I said, if you use matrix operation, you don't need a for loop. So the first thing you need to do is you use diagonal lambda. So if your lambda is a diagonal matrix, if you use that DIAG function, that will create a column vector which only has the diagonal terms in this column vector. So if this is m by n, then this is m by 1 after DIAG function. All right. So then how can we create something like this? We already know our Q naught vector. So the way we create a Q in MATLAB is exponential function to diagonal. So let me name these as something different. Let's name it as what I can use. Let's use an E matrix or E vector. So this is your E vector. And then times T dot product dot multiply Q naught. So what we're doing here is we're using a dot multiplication in MATLAB. So you can get rid of these for loops. So whatever box in this blue box would be equivalent to this red box. And then remember the blue box is 100 times or n times faster than this red box. All right, so what this dot product is doing is if you have A vector is A1 all the way to AN, your B vector is B1 all the way to Bn. Your A dot product B, it's actually not dot product, is that? It's dot multiplication in MATLAB. So it's just, you need to, so it would do, let's do a column vector. So what it does is it just calculate the multiplication entity by entity. So that's what dot multiplication is doing in MATLAB. So let's look at the equations we have. So we have Q vector equals to exponential E vector T dot product Q naught. Let's look at what we have on the left-hand side, on the right-hand side of these dot multiplication. So on the left-hand side, you have exponential function to the lambda 1 t, lambda 2 t, all the way to e lambda n t. On the left right-hand side, you have q naught 1, oops, q1 naught, q2 naught, and then all the way to the last one, qn naught. Remember, after dot product, you just have the multiplication entity by entity is e lambda 1 t q1 naught, e lambda 2 t q2 naught, all the way to e lambda n t qn naught. So as you can see here, this dot multiplication gives us q solution. So the benefits here is you don't have any for loops, right? So that's method 1.3, and then you can check these out in my MATLAB code. I highly suggest you to apply all the method you learned to homework number 2. It should be relatively easy. Right? So method 1.3, you can see that we first find out eigenvalues and eigenvectors of A, collect initial conditions, find the initial conditions in Q domain, and then we find the solution in Q domain just by using dot multiplication. The left-hand side is just what I mentioned there, and then right-hand side is the initial condition in Q domain. And then after that, you just need to multiply these coordinate transformation matrix so that we can dump solution from Q domain to Y domain. And then eventually you can plot it. So, and also I want to highlight is the method 1.2 here is not working. So then you can see the limitation of this method. And eventually that's the solution we have. They look identical. That's because they are giving us, so these two solvers are giving us identical solutions. All right. So that's all the method we learned that targets state space representation. Make sure you try these out in homework number 2 and number 3. Let me know if you have any concerns in next lecture. That's all the new stuff for today's lecture. So I think I still have about 15 minutes to answer any questions you have for project 3.
Will you be posting the examples for this lecture? The MATLAB examples?
Oh yeah, it's already there. It's already on the Blackboard.
Never mind. Forget I asked.
Yes, because I just posted too late. I did I solved all of these this morning. So it should be found.
No worries then.
Yep. All right. So for project number 3, can you explain FBeamCon a little bit? Yep. Yes, the FBeamCon, that's something. So last semester, I asked all the students, last year actually, I asked all the students to use FBeamCon, but it's not fun. So let me explain this to you.